All right, static friction. So we've already determined that there can be a maximum static friction, and at that point then it will, if it goes any above that, then it will start to slip. This is saying a static friction force greater than maximum static frictional force is not physically possible. So if you are going to solve for the maximum static friction, you would use this thing called the coefficient of static friction, which is unfortunately the same symbol as what we use for micro. You know, when we were doing the metric scale, it's kind of that funky looking U with the tail in the front. And with the subscript S to specify that it's static friction, because we also have coefficients for kinetic friction and rolling friction. And then it's being multiplied by the normal force. Well, in most situations, weight is equal to normal, right? If it's just sitting on a table, if there's just an object that's sitting on a table, okay, there's an amount of force that's pulling down, gravitational force is pulling down, there's the amount of normal force that's pushing up. These should be equal, assuming that nothing is moving or accelerating, okay? So this quick check is saying you've got a some sort of rope or something that's pulling this box that's 100 newtons and it's at rest, and it's pulled by 30 newtons of force. So it wants to know if the box moves. Well, it's giving us coefficients for both static friction and kinetic friction. Well, before we can really get into the kinetic friction, we need to see if it can go past the static friction, then we can start messing with kinetic friction. If it's moving, then we can start messing with kinetic friction. But at this point, we need to see if it can even move with 30 newtons of force. So we have to use our equation that we just got. So we have our coefficient for static friction here of 0.4 times the normal force. Well, the box has a weight of 100 newtons. So, like I said before, if it's in a normal situation, which it is right now, it's just on a table here, so it should have the same normal force as it does gravitational force. So that means that its normal force is just 100 newtons. Well, if you multiply that, then that's 40. Well, 40 is greater than 30. So can the box move? No, because its static friction is still bigger, okay? It's more force than the force that it's pulling it. All right, now that gets us to kinetic friction, which is a force that's proportional to the magnitude of the normal force, and it does also have a coefficient of kinetic friction. The kinetic friction direction is opposite to the velocity because it's opposing. We've talked about friction is usually, it's opposing whichever direction it's going. And for any particular pair of surfaces, the kinetic friction is going to be less than the static friction. Okay, now you can see based on this free body diagram, probably shouldn't have drawn that in red because the free body diagram's in red, but you can see that the tensional force is greater than the kinetic friction, which means that you're going to have a net force in the positive direction. So this is a situation where something is accelerating, okay? All right, so now this is saying if you have a box that's being pulled to the right over a rough surface and tension is greater than the kinetic friction, okay? So like this situation, like this free body diagram right here, So the box is speeding up because it's greater, it's accelerating. Suddenly the rope breaks. Well, what's going to happen to the box? Does it just stop immediately? Well, no, because it has some sort of momentum that's going to, make it go for a little while. Does it continue with the speed it had when the rope broke? As soon as the rope breaks, that speed is going to decrease. Does it continue speeding up? Well, I just sort of said that doesn't happen. Does it keep its speed for a short while, then slow, and then stop? There's too many things going on there. As soon as that breaks, it's just going to it's going to slow steadily. It's going to be a constant deceleration at that point until it stops completely. Okay? Now this is a little bit different situation because you've got this box, and instead of this rope being pulled like this, it's now being pulled on the top right corner. So what's going to happen then? Typically, if the box was just sitting there, right, then the normal force and the gravitational force are equal to each other. Well, because of that tensional force right here pulling up on it, it's not going to have the same amount of normal force because there's this force that's sort of pulling up on that box. It's still going to have gravitational force pulling down because it still has weight that's constantly pulling down. But what is happening to the normal force? Well, because of this right here, it's taking some of that off of the normal force. So the normal force is actually less than the gravitational force in that situation. All right, and now we get to rolling motion. So if you slam on the brakes hard enough, your car tires slide against the road surface and leave skid marks. That's kinetic friction. But a wheel rolling on a surface also experiences friction, but not kinetic friction. So it's kind of hard to distinguish between the two because they're both moving, but one is moving in a circular motion, a rolling surface, where the other one is experiencing kinetic friction based on, this point right here. So this is saying that the wheel is stationary across the area of contact, not sliding. And the portion of the wheel that contacts the surface is stationary with respect to the surface, not sliding. And so that is known as rolling friction. And it too also has a coefficient constant times the normal force. And all of these, have been determined based on materials. And this particular table might be useful for homework purposes. Of course, I would think with the online homework that it would probably just give you these values within the problem, but just in case, you might need to have this available. Just sort of tells you, like for instance, rubber on dry concrete versus rubber on wet concrete. So that completely changes the kinetic, static, and rolling frictions. So if we would have been face-to-face this week, or really last week, we would have done a lab where we would have actually done wood on wood, and we would have tried to prove actually these two values with wood blocks on a wood board. But so far I have not been able to find a simulation for that. So if that is still the case, then we will not have a lab over that. I'm sure you're devastated on that. But anyway, you will maybe need to use this information for homework purposes. All right. This graph here is good just to show that, you know, you can get to this maximum, you know, static friction, and once it slips, we said that the kinetic friction is less than the static friction, and kinetic friction doesn't increase. We were showing that, you know, you could pull on that rope and the static friction would be the same, and you could pull on the rope some more and the static friction would be equal. So we could see that that actually increased. But once it slips, the kinetic friction just maintains a constant as the object moves. Oh, okay, so this is an example. And this is example 6.5. So, okay, let's see. I have to go to Chrome here, the eText. Oh, I've signed out. Okay, I'm gonna stop this.